All right, hello physics. I'm going to be doing projectile motion in this video. If you want to try and follow along, I'm going to be using the problem described, or the scenario described, in problem 23 in the textbook. That's on page 77. So if you want to try and follow along, if you want to see the problem that I'm actually working on, see what I'm reading, that might be helpful for you. So if you want to pause this and pull that up, question 23, page 77. All right. So a student stands at the edge of a cliff and throws a stone horizontally over the edge with a speed of 18 meters per second. The cliff is 50 meters above a flat horizontal beach as shown in the figure. Okay, that's the information that I'm going to use. And then from that, we are going to do a couple of calculations. We are not actually going to be looking for the answers to the questions that it is asking, because it goes kind of into extra details that I don't want to deal with for this. But it's a really good projectile motion problem, so we're going to use it. So first things first, we are going to draw a picture. Weird, right? All right. So we have a cliff, a student on the top, and he throws a rock or something, an object, and it goes out like this. And pretend that's a horizontal line and not actually a sloped line. Okay, and we are given a couple pieces of information. We are given the height of the cliff, SY. Actually, I'm just going to put H, and then I'll go into that later. So the height of the cliff is 50.0 meters, and the initial velocity of the rock, we are told, is a number that is slipping my mind at the moment. 18.0 meters per second. And those are the only two pieces of information that we are given. And from that, I want to determine how far from the base of the cliff does the rock land. So the first thing we need to do to really actually start to solve this problem is we need to draw a little table. Now this is a table, this table will not be of any use to you if there is no acceleration in the problem. There has to be acceleration. If it's not acting as a projectile, this table will be worthless to you. Okay? And the table simply lists x and y values for those same 5 variables that we have been using. And I'm having trouble reaching this. So I'm going to step back up on my stool because life was easier when I was using it a second ago. There we go. So we have VI, VF, S, A, and T. Now, we're talking about projectile motion, which means that we have motion in 2 dimensions, and that table's too small. Hang on, I'm going to pause this, and I'm going to make that table bigger. All right, that might be a little excessively big, but we're going to deal with it. So we need to recognize that motion in 2 dimensions are measured separately. Okay, if I toss this marker and it travels in an arc as a projectile, assuming my hand is not here, but it's traveling through this motion, it is going to have a vertical motion where it rises, stops, and then comes back down, and it's going to experience a horizontal motion where it travels to the side in a straight line. Okay, but both of those motions are happening at the same time as it travels in an arc, but we can measure them separately. So when we look at this problem, the first thing that you really need to pull out is this thing right here, the 18 meters per second. The object is thrown horizontally at 18 meters per second, which means that this is not the total velocity. This is not a vector that has to be broken up into components. This is just the x component of its motion. So the x component of the velocity is 18.0 meters per second. Okay? And then we also have the height of the cliff, which, according to the problem, this is horizontal, not sloped like it is in my crappy picture, but horizontal. The rock is going to fall then 50 meters. So that is a displacement, a distance. That is the vertical distance that has to be traveled. So SY is 50.0 meters. Now at this point, we only have two pieces of information, and this is not enough to solve this problem. So we have to be able to pull more information out of this based on what is written. So for that, we have to look at some of the things that we're given. Okay, we are trying to find, ultimately, this number, which means we have to have two of these numbers in order to solve it, which shouldn't be that hard to do. Let's look back at projectile motion. There are two things that we know are constant in projectile motion. That is the acceleration in x and the acceleration in y. Okay? The acceleration in x for a projectile is always 0. For a projectile. Not for everything, just for a projectile. And that is just one of those numbers that you need to know. The acceleration in x for a projectile is always 0. Well, since this is 0, that means that the final and the initial velocity have to be the same. Okay, well, that doesn't really get us anywhere right off the bat, because we still can't find s with what we've got here, because we have to have t in order to get s, or we have to have an a. And since a is non-existent, we can't use the first, or we can't use the second equation, and since v is constant, or a is 0, we can't use the first equation. Which means that, and this is true most of the time, when we're working with projectile motion, true most of the time. There shouldn't have been a pause there, so I'm going to say that sentence again. This is true most of the time when working with projectile motion. You are going to be using the third kinematic equation, and that is S equals VIT plus AT squared over 2. In x, this is 0. Which means that we only have to worry about this side of the equation for x. So we can use this in order to get our distance that we want. But we don't know t. Well, think about this. If this marker travels in the arc that I described earlier, which takes longer? The time for it to rise and come back down, or the time for it to travel horizontally to the endpoint? I'll give you a hint. It's a trick question. It's the same. It takes the same amount of time because it's actually one motion. It's just being broken up into two different directions. If you look straight down on this motion, then it looks like it's moving like this. If you're looking at it from this side or from this side, it looks like it just goes up and comes back down. But both motions take the same amount of time because they're happening at the same time. This is the key to projectile motion. Okay, both the horizontal component of the motion and the vertical component of the motion must happen at the same time, in the same amount of time. So we can use y to figure out the information in x, specifically the time, because there's only actually one number here. No matter what, t has to be the same for both x and y. So let's look at y. Uh-oh, we only know one thing in y. That's even less than we knew in x. Well, hang on, let's take another look at this. We said that the acceleration in x for a projectile always has to be 0. But what about the acceleration in y for a projectile? Well, that always has to be 9.8 downward. So this is going to be 9.81 meters per second squared. I'm using the 1 because it's the third sig fig for the acceleration of gravity. It's given in your textbook, but we haven't been using it because we haven't been worried about sig figs. So 9.81 is what I'm using and what you should be using from now on. But that's still only 2 things. We have to have 3 in order to make any kinematic equation work. We have to know 3 things. Well, let's go back to our initial velocity. We're told that the student sidearms this rock, kind of like skipping a stone, so that he sends it out with perfectly horizontal motion at the beginning. Well, if it's traveling perfectly horizontally, what's its vertical velocity going to be? How quickly is it moving up or down if it's traveling like this? Well, it's not moving up or down at all. The initial vertical velocity for this problem has to be 0 because it is traveling horizontally. Now, if it was traveling with an angle, we would have to break the initial velocity up that they gave us into a vertical and horizontal component. But that's not the case in this problem. We are just given the velocity and said, this is only horizontal. We're told, we're not said. We're told, this is only horizontal. So this has to be 0. And if you're wondering why 0 and 0 are 0.00, it is because 0 in this case is an integer. It is exactly 0. So we can put as many sig figs on that 0 as we need to make our calculations work. Now we have 3 things. Now we can do some fun stuff. We can actually calculate this. Now, we want t, which means that the shortcut here is going to be to use the dreaded third kinematics equation and deal with the quadratic. But I have good news. We don't have to deal with the quadratic because vi in y is 0. So S equals VIT plus AT squared over 2, but this is 0, so S is actually just equal to AT squared over 2. We do a little algebra with that to solve it for T, because T is what we're trying to find right now, and I'm going to switch colors. And we get that T is equal to 2S over a times, or square rooted times. Why am I trying to do multiplication here? And I do not have a calculator handy, so I'm going to go get a calculator real quick. I'm not sure where mine is. Got it. Okay. So first thing we need to do is plug in our numbers. So T equals 2 times S. Now this is S in what dimension? It's S in Y. We're doing a problem in Y, so I'm actually going to add a Y to these. So that is going to be 2 times 50.0 divided by the acceleration in Y, which is 9.81, and then square root of all that. So on square root of 2 times 50, which is going to be 100, divided by 9.81. And that gives us a T of 3.19 meters, good Lord, seconds. Okay, now that is not our final answer. That is just this number. And that is our time for both the vertical component and the horizontal component. So now we can go back to this equation where this part is 0, and we can calculate our S, our horizontal displacement. So S is equal to VIX times T, because this is SX. So SX is equal to 18.0 times 3.19. Which gives us a horizontal distance of 57.4 meters. And that is the basics of a projectile motion problem. I'm going to step off the screen so you can take one last look at what I've done here. The numbers in black were given to us directly. The numbers in purple, I don't know if you can tell, they are the numbers that we were able to infer or assume based on information in the question. They were not given to us directly. And the two blue numbers, this one and this one, are the two that we calculated. Everything else we were able to figure out based on what was given to us. This equation is your best friend in this chapter, in this unit. That is the equation you are almost always going to be using. Okay, because one side of this is almost always 0. Now, if for some reason VI is not 0 and you're trying to get T, you can always calculate VF and then using the first equation. No, using the second equation, the second kinematics equation, you can get VF, and then you can use the first kinematic equation to get T. If you really want to avoid that quadratic. But most of the time, this is the equation that you're going to want to use. So that is it for this video. Again, I'm going to step off so that you can actually see what's going on here. I hope this helps, guys, and I will see y'all back tomorrow.